Hello. Hey, so I'm Mike Solomon, and we're going to be talking about transpiling GraphQL instead of writing customized server code. Before we jump in, I just want to clear up the meaning of transpiling. Transpiling just means that we're going to be taking some source code. In our case, it'll be a GraphQL query, and we're going to translate that into some different source code. And today, that'll be JavaScript-flavored pseudocode. Little quick background about me. I work on a team at Twitter that builds a data access layer as a service that we use to power our GraphQL implementation. And you can follow me at msol on Twitter if you want. First, a quick agenda, just so you can know what to expect. Today, we'll recap some properties of GraphQL that are relevant for transpiling and introduce an example. We'll talk about how GraphQL implementations typically work and which parts a developer is expected to implement. And lastly, we'll talk about how we can skip doing pretty much all of that in favor of letting the computer do it for us. All right, so now that you're trapped here, my real purpose is to get some engagement on my tweets. So if you go to this URL, then you'll see something like this. There's a series of tweets. Each one's a vain attempt at humor. And they all belong to a user. In this case, that's me. And because this is a timeline of tweets that all belong to a user, we call it the user timeline. Very creative. And you can see it's made up of tweets. So tweets in a timeline called a user timeline all belong to a user. Hopefully everyone's tracking so far. So we're going to jump to a little bit of GraphQL. And I don't know how familiar all of you are with that, but hopefully it won't be so bad. Let's look at how we would model this in GraphQL by looking at a simplified schema definition. So you may or may not be familiar with how GraphQL schemas look, but it's basically all of the types that are available in your API. So this is a very simple API that only lets us query for one thing. So you can see here we have this type query. This is going to contain all the things that you can query for. So today, that's just going to be a user. So we see we have this user, and it takes an ID, a user ID, and you're going to get back a user. And then we can see we have this user type. You can get that same ID back. And you can also get a timeline. That's going to be our user timeline, which we saw in the last slide. And maybe the type, the way the type's written here might not be familiar to you, but that basically just says that it's a list of tweet objects. And we can see there on the right, the type of tweet is just an ID and maybe a text field that contains the text of the tweet. Of course, real tweets have a whole lot more than that, but we're just going to keep it simple today. OK. So let's look at a query demonstrating how we might actually get data for this in GraphQL. So in GraphQL, your queries start with query. And then we can give it a name. Here we'll call it user timeline, again, staying very creative. And we'll pass in a user ID. So if you're going to look up my user timeline, you'd pass in my user ID. Then we want to actually query something on that user object. We want to look up the user. So we'll take that user ID and pass it to the user. And then for that user, we want to look up their timeline. And then for every item in that timeline, because remember, it's a list of tweets, we want to get back just the text field for each of those tweets. So for the user timeline, we're going to look up a user, the timeline associated with that user, and then the text associated with each tweet. So even if you're not familiar with GraphQL, hopefully this is enough to kind of like get you started. And you'll notice here that there is lots of what. So there's the user, there's the timeline, there's the text, but nothing here says how to do it, which is good in an API. It shouldn't be telling you how you're fetching things. But someone does have to eventually write something that will actually go and get this data. So let's belabor this point a little bit more with a diagram, and we can focus on where the data comes from. So we start with a user ID, and we're going to use that to get the user from some database. Maybe it's from a service, but I'm just going to say database and not distinguish, because it's actually not that important for what we're talking about. Once we have that user, we can then look up the timeline associated with that user. And for that, every entry in that timeline, there's going to be a list of probably tweet IDs or something. We can go and look up the actual tweets. And then on each of those tweets, there will probably be a text field that actually contains the text of the tweet. So there we don't need to go and talk to a service. We can probably or a database, we can just get it off of the objects directly. So this is kind of like where our data comes from. And this is probably, there's probably a lot more data available here. But this is just the part of the graph that we're concerned about for this one query. So let's talk a little bit about how GraphQL implementations typically work. So if you have a GraphQL service, the odds are good that you wrote some code to actually go and fetch some data. So let's go over what functions we might implement to get data for each field in our query. These are usually called resolvers. So we'll look at examples in something that resembles JavaScript, and we're going to assume that we're working in some GraphQL framework, the details of which aren't actually important. So we'll start by writing a resolver for the user field in our GraphQL's top-level query object. So you can see here that this takes 3 arguments. There's the parent value, which is query. Here, that's actually not that useful. Also, the field arguments, which here is called args, and also a request context. This is usually just a place where there's things like it gives you access to things like the logged in user, maybe access to databases and things like that. So let's look at the implementation of this function. It'll probably look something like this. So we'll take, you can see on the right there, we pull out the ID argument that was passed in, and we're going to take that and pass it to some database accessing function that's on our context. So we'll take the user ID and we'll use it to look up a user by ID. Nothing very earth-shattering here. Okay, we also have a couple more of these that are going to do very similar things. You can see that for timelines, we use the user ID to look up a timeline in a different database, this one that contains the timeline and tweets. And in this last function, for the text field, we just pull it off of the parent object, which is a tweet. So you can see that first, there's a different name for the first argument in each of those that kind of like represents what the parent object is, and you can access data on that. So sometimes we're looking things up in databases, sometimes we're just pulling things off of objects. So where does the data come from? So we've kind of seen how you might implement resolvers by hand. So here's that same code again from the last slide. But how do we actually know where the data comes from? So here it comes from a database. And here it comes from either a different database or maybe a different table or a different service or something like that. And here it just comes from a field on the tweet object. So some of this knowledge is baked into these resolvers. Each of these functions are called a resolver. But it doesn't have to be, because in GraphQL you also have a schema, which tells you the types of all the data that's available in your API. So it'll tell you, for example, whether something is a union or a list or an object. So a tweet's an object, whereas a timeline is a list of tweets. The schema actually tells us more than that even. It also tells us about graph connections. So for example, we know that a user has their own timeline. That's actually a graph connection, as we saw a couple of slides ago. So these graph connections are always by type and ID. So for example, we might have a user ID. You can look up data associated with users that have that ID. Not too surprising. And if we need some extra information, maybe just the user ID isn't enough, then we can use field arguments to pass in extra information. That's just kind of a side note. Also, we can enrich the schema with extra information. So, of course, it's going to contain all of the type information and stuff we saw when we looked at the schema earlier, as well as information about graph connections. But we can also add extra information if we want. So one example is we might add information about how to call into a database or service for a particular entry in the schema. And the source of that information might be something like an existing data access layer. Maybe I'm projecting here because I work on such a service at Twitter, but these sorts of things do exist. Okay. So now that we've seen how GraphQL implementations typically work, let's see if there's anything that we can improve upon. So we're using GraphQL to make life easier for developers. So we want it to be trivial to add new data to our GraphQL API. So that seems like a pretty good goal. We've seen here that the resolver code seems kind of repetitive. So maybe that's a hint that we can avoid writing it at all. Maybe there's an opportunity to just skip that step entirely. Another goal is no business logic in the API layer. So we found that teams can have more independence if business logic doesn't live in the API layer. Resolvers can be a really tempting place to put that logic because you're actually writing code, and maybe it wouldn't be so bad if we just verified a couple of things right here in the API layer, and then soon maybe we pull in some extra data, and then we can verify that those things are working together as expected. And just having that place to write logic makes it really tempting to start adding business logic in your API layer. Another thing we might be interested in is API updates without deploys. So updates typically require deploys, and that's not always a big deal, but they do represent an organizational dependency between the team that owns and operates the GraphQL service and a team that might own and operate the access to the underlying data. So maybe we can give teams even more independence if we don't require the GraphQL service to deploy whenever they add new data. Obviously, if we're writing resolvers, probably need a new deploy so that we can pick up that code. And lastly, we want to make sure that things like error handling and access control and any sort of improvement that we might dream up in the future gets applied everywhere without users doing any extra work. If we can apply things automatically, then users can't forget to do them, or sorry, developers on the GraphQL API can't forget to do them. So that leads us to this idea. Maybe we can generate most of our implementations instead of writing them. So instead of writing resolvers for each field, maybe we can take every query that we get and transform that query into a specialized function with enough logic to fulfill that query and just that query. So if that sounds a little crazy, it's worth remembering that most queries are reused many times. So doing this translation is maybe an acceptable price to pay. This would mean we would have no handwritten resolvers. And we would be automating a lot of this. So it would be ideally very little work to add new data. Maybe we just put enough information in the schema to actually get the data and know what type it is, but then you don't have to write code for it. And this would also make it easy to apply our good ideas everywhere. Because we have a place where everything's being generated, that's nice and centralized, we can add error handling, access control, things like that that might apply everywhere. Okay, so let's go back to our query. So here's the same query that we saw before for getting the user timeline. So we're going to go through this line by line and see how we can generate code for it as if we were the transpiler. So the code that we'll generate will look something like sudo JavaScript. And remember that everything hereafter isn't code that we'll be writing by hand. We're going to see how we can automatically transpile these GraphQL queries into functions without further human involvement. Okay, so let's jump into the very top. So here we have a query named user timeline that takes a user ID argument, and it has a body that we're ignoring at the moment. That's what that 3-dot ellipsis is for. So this is going to become a function. So let's be very creative, and we can give it a name like getUserTimeline, and it's going to take one argument. So I think this will be easier to follow if we can actually see this side by side. So let's put our GraphQL query on one side and our generated code on the other side. So here we have our query, the user timeline query, and this is going to generate our getUserTimeline function. So we also still have the rest of the query still to fill in there on the left, and we have some corresponding code to generate as well as a return value that we haven't generated yet over on the right. So this is just the basic shell. We're taking a query and we're going to turn it into a function. This is something we can do automatically. Okay, so moving on, objects that are looked up by ID. So here you can see we're looking up a user by the user ID. We're passing in just that one argument. In this case, this is going to be translated into a call out to a database. So here we might do something like database.user by ID and pass in that user ID. So let's look at this back in context, where over here on the left, we're asking for the user by ID, and on the right in the function, we're actually getting the user from the database. And we still aren't worrying about the rest of the query over on the left. And on the right, we can actually start building out the value that we're going to return. We know that we have to return a user, so we can name it user. And here you can see it's kind of like a JSON-esque return value, but it could also be some richer type if we were using some other language. Okay. So now things are going to get a little bit more interesting. So graph connections like timeline, and if you remember from our diagram, users each have a user timeline. So this actually is a graph connection. Well, in order to generate this line, or in order to generate code for this, we have to know that users have timelines. And we actually do know that because of how the schema is structured. We know about that graph connection. So here we can generate a line of code like this, where we look up the timeline using that user ID from the parent object. So we're not actually done with timelines yet, because timelines are lists of tweets. And we need to deal with that aspect of it as well. So for lists, when we look up timeline, we know from the schema that a timeline is a list of tweets. We need to iterate over the results and do something for every item in that list. So we can generate some code like this, where we map over the timeline and do something for every tweet inside it. All right, let's put this back in context so we can actually maybe understand what's going on. So we're focused on the timeline, and we can use the schema's graph information to know that we need to look up the user's timeline in the database. And then we can use the type information from the schema to know that we need to iterate over every item in that timeline. And that's actually all we want to focus on for now in the query. But now we know that the value we're returning has a timeline nested inside the user, and that the value is the result of iterating over that timeline. So we've actually filled out most of our final return value there already. We know that we're returning a user that contains a timeline that's made up of tweets. Okay, and the last one's pretty easy. So for field access on objects, which looks something like this, we're just looking up the text field on each tweet. That's going to remain field access on objects. So our code is just going to pull out the text field from the tweet object. So now we can add the text field there on the left, and now we can actually see that this is the whole GraphQL query we were trying to transpile in the first place. And in context, it's easy to see that we can just pull out the text field from the tweet so that we can return it. And we're still returning the same overall value from before. So we now have our original query on the left and our generated function on the right. This function is only used for this query, not for any others, and nobody had to write this code. Instead, we generated it using type information and a little bit of extra information in the schema to tell us how to access like where the data lives for looking up things in databases. And you can see that it at least somewhat resembles the code that you might write by hand here. If you were going to write a function to serve just this query, it might actually look something like this. We have user, timeline, text, all in roughly the same order we see them in the query. So in some sense, the query on the left is the declarative version of the procedural implementation on the right that we generated. All right, so now we've seen how we can automatically generate implementations for queries. So let's go back and see how we did on our goals. Let's see what this enables for us. So now we've made it possible for us to build a system with easy opt-in to GraphQL for data sets. We haven't built that whole system here. We just did the transpiling piece, but we've kind of opened the door. Because we eliminated the need for developers to make changes in the API layer, building a system like that will be a lot easier. Remember that we can use a data access layer that tells us where the graph data lives, so it's easy to augment the schema and wire up new connections like this dynamically. There's also no business logic in the API layer here. Because this is totally generated, there's just no place to even do that. And this has opened the door to adding new data to GraphQL without deploys, because we just need to update our schema with new information. We don't actually need to write new code that needs to be deployed. All right. We're also able to generically apply some things, such as error handling. We can generate error handling logic in the query, so it's easy to see how it works, and we can't forget how to do it. We skipped over that here just to keep it simple. We can also generate access control, another thing we can't forget about. And it's not obvious from these examples, but we can actually also generate code that handles batches of requests. So in this example, if you wanted to look up a whole list of tweets, we could actually ask for all of the tweets in a single request instead of many. Lastly, it's also easy to add new operational improvements generically in this model. Maybe we could add some retries or something like that. OK, so what next? What else does this open the door to in the future? So because each query becomes a specialized function, we have lots of information about what a query is going to do, which makes it a good candidate for optimization. Also, this approach extends naturally to mutation and subscription support. So we only looked at the read side today, but if you want to do writes or if you want to do streaming information, then a lot of this would still apply. All right, that definitely glossed over a lot of details, but there's probably some other ways you could approach some of these problems. So if you'd like to talk to me about that, then I'd love to talk to you after this. Again, I'm Mike Solomon, and you can follow me if you like tweets. I'm msol on Twitter. And thanks for listening. I think we have time for a couple of questions, one or two. OK, so the question is, what changes when the mapping between the graph of where the data actually lives isn't quite so simple? Do you have an example in mind? OK, so if the data is spread out across many different places and we need to fetch it independently from each other, all of the composition is done by the GraphQL service. So kind of its job is to go out and actually fetch data from all of these various services and put it together into a final result, which is kind of like what the code we looked at generated. So I guess we haven't come across too many examples where we can't do something like this. Most of the time, you're actually just going out and fetching data from either for a list of data or for single items. And you can actually just map pretty much your query exactly onto your actual data dependency graph. Can I show the code that generated the code? Okay, so how did we actually do this? Because we didn't actually look at the code that did any of this work. So it was not just string manipulation. We actually have in our case, we're actually targeting an internal language, a query language that we have at Twitter. So we already had some tools around manipulating that. And then we basically walk over the AST of the GraphQL query and then do some intermediate transformations and then eventually spit out our target language. I know that's really hand-wavy, but sorry, I don't have any examples with me. Second. Okay, so how do we inject a test database if we don't want to run this against our real production data? I think you could generally do that in your context. So each one of these resolvers, if you were writing it by hand, in the resolver you would connect that to a test database instead of your real database. I think that same basic idea would still apply. You could just connect it to a database. You could just change what database it's connected to, as long as it has the same, schema. Of how it does this. So you want to know how this transformation actually happens? Or what happens thereafter?
Like how it actually happens. How does the GraphQL
Sorry, I think I'm not totally following. Okay, so the left-hand side actually isn't an AST, it's actually the original GraphQL query. But this is executed within a schema that has, we also have type information about all these different pieces. So using the type information plus this query is enough information to generate everything on the right. Does that answer your question? Cool. All right, I think we're out of time for questions. Thanks for coming, everyone.